Hi, Assalamualaikum. We are from Higgs Hive Group. And this is our member.
First things first, what is the Higgs boson? Higgs boson is a fundamental particle in the standard model of particle physics. Its discovery in 2012 at CERN using the Large Hadron Collider, which is LHC, associated with the Higgs field, which gives mass to elementary particles. Next, what is the role of the Higgs boson? First, as Higgs field, which means an invisible energy field that fills space. Next, as a mass generation, particles acquire mass by interacting with Higgs fields. Last but not least, explain how particles like quarks and leptons get their mass. Next, discovery milestone. First, proposed in 1964 by Peter Higgs and Francois Elite. Then, confirmed experimentally in July 2012 by CERN. Then, data collected from high energy proton collision at the LHC showed evidence of the Higgs boson. And then, Nobel Prize in Physics, which is 2013, awarded to Peter Higgs and Francois Elite for the discovery.
Higgs mechanism. This is a fundamental process in particle physics that explains how certain particles acquire mass within the framework of the Standard Model. The Higgs mechanism explains how particles acquire mass in the Standard Model without breaking its fundamental symmetry. It introduces the Higgs field, an invisible field that permeates the universe with a constant, non-zero value. As particles interact with this field, they gain mass based on the strength of their interaction. This process, known as electroweak symmetry breaking, split the unified electroweak force into the electromagnetic and weak forces, giving mass to particles like the W and Z bosons, while leaving photons massless. The discovery of the Higgs boson in 2012 confirmed this theory, making the Higgs mechanism a cornerstone of modern physics and essential for understanding the universe's structure. Discovery of the Higgs boson. The first one is the significance of the discovery, and then the second one is the theoretical background. The discovery validated the Higgs mechanism and completed the Standard Model, a key framework of particle physics. Francois Elite and Peter Higgs were awarded the 2013 Nobel Prize in Physics for their theoretical work on the mechanism that predict the Higgs boson. The discovery opened doors to explore phenomena beyond the standard model, such as the dark matter and supersymmetry. For theoretical background, theoretical physicists like Peter Higgs, Francois Elite, and others proposed the existence of the Higgs field and its associated boson to explain how actually particles acquire mass. The Higgs boson became a crucial component of the Standard Model, predicted to be a particle resulting from the Higgs field. However, its existence remained unconfirmed for decades. Continue for the discovery of the Higgs boson. The third one is the Large Hadron Collider, like you see, operated by CERN in Geneva, Switzerland, and then they are designed to recreate high energy conditions like those just after the Big Bang. LHC accelerate particles to near light speed and collide them. Two main experiments, which are ATLAS and CMS, were built to search for the Higgs boson and investigate other fundamental questions in physics. The last one is the discovery process, which are preparation, hunting the Higgs, and breakthroughs. Alright, the LHC began operation in 2008 but faced initial technical challenges. But by 2010, it started colliding proton at high energy. Hunting the Higgs, physicists analyzed millions of collision events to look for signature for the Higgs boson. And then the last one is breakthrough. CERN announced the discovery of a new particle with a mass of around 1 to 5 GeV, and both the ATLAS and CMS experiment observed signal consistent with the Higgs boson, confirming its existence.
Next is significance in Standard Model. What is Standard Model? The Standard Model describes how the universe works at its most basic level. It is a framework in particle physics explaining the fundamental particles and forces, and also developed and formalized in the early 1970s. And why it is important? It is important because it explains the interactions between matter and forces, and also provides the foundation for modern physics experiments and discoveries. Next is the building blocks of matter. So first, the Standard Model identifies 12 fundamental particles, which is 6 quarks and 6 leptons. Example of 6 quarks is up, down, charm, strange, top, bottom. It's combined to form larger particles like protons and neutrons. For the 6 leptons, examples is like electron, muon, tau, and their corresponding neutrinos. and include particles like the electron, which is essential for forming atoms. These particles are considered indivisible, meaning they cannot be broken down into anything smaller and are recognized as the most fundamental building blocks of matter that form everything in the universe. Next is the fundamental forces of the Standard Model. So the universe operates under 4 fundamental forces, which is gravity, electromagnetic force, strong nuclear force, and also weak nuclear force. For the gravity, it is responsible for attraction between massive objects like planets, stars, and it is not fully explained by the Standard Model. For the electromagnetic force, governs the behavior of charged particles like electrons in atoms, and the key to electricity, magnetism, and light. For the strong nuclear force, it is binds quarks together to form protons and neutrons, and holds the nucleus of an atom together. The weak nuclear force, it is responsible for radioactive decay and nuclear fusion in stars. After that, we have predictive power of the Standard Model, which is the Standard Model has successfully predicted the existence of many particles before they were discovered experimentally. So, the example is prediction and discovery of the W and Z bosons in the 1970s until 1918s. And the other example is prediction and confirmation of the Higgs boson in 2012. So, second is the experimental success, which is the Large Hadron Collider (LHC) at CERN plays a key role in verifying this prediction. So next, we move to the detection technique. Why detection matters? It is because the Higgs boson was the missing piece of the Standard Model, and it is confirming its existence required advanced techniques and technologies. So second is the key players in detection, which is the first one is the Large Hadron Collider or LHC, and specialized particle detectors and method. So next is the Large Hadron Collider, or we can call it as LHC. So what is the LHC? So it is the world's largest and most powerful particle accelerator. And the LHC is the most advanced scientific instrument ever built for studying subatomic particles. It is a circular tunnel measuring 27 kilometers in circumference, designed to accelerate particles to near light speeds. And it is located underground at CERN, on the border between Switzerland and France. How it LHC works? So the first is accelerates protons to near light speeds. Inside the LHC, protons, which is a type of particle found in atomic nuclei, are accelerated to speeds approaching the speed of light. This is achieved using a series of superconducting magnets and radio frequency cavities that kite and energize the particles. So, collides protons to recreate conditions similar to the Big Bang, which is two beams of protons traveling in opposite directions are made to collide at specific points in the accelerator ring. And this high energy collision generate extreme temperature and pressures, recreating the condition present a fraction of a second after the universe began. The detectors surrounding the collision points capture data about the particles produced in these events, allowing scientists to study their properties and behavior. And what is the purpose? The purpose is to generate a high energy collision to produce rare particles like the Higgs boson. The LHC's primary objective is to replicate conditions that existed shortly after the Big Bang. This is achieved by colliding particles at extremely high energies, creating an environment where fundamental particles, including the elusive Higgs boson, can be observed. This collision provide insight into the fundamental building blocks of the universe and validate prediction of the Standard Model. So next is the detection methods, which is the detection of the Higgs boson involves tracking its decay product, as the particle itself decays almost instantly. These decay products are detected using advanced particle detectors at the LHC. The challenge is to differentiate these decay products from background noise, as they are common in other particles collision. Specialized methods such as comparing the observed patterns of particles like photons or muons with predicted outcome help confirm that Higgs boson's existence. These decay signatures are compared against expected patterns from the Standard Model. The Higgs boson is identified by matching these patterns to the rare decay events observed in the collision data.
Practical application of Higgs boson discovery. Firstly, advances in particle physics research. Secondly, technology development. The implications of Higgs boson discovery. Firstly, future physics exploration, such as exploring quantum gravity and unifying forces. Next, education in public engagement, such as inspiring a new generation of scientists.
This is references that we will use. Thank you.